Our Lewis picture is very qualitative in nature, and it tells us how many bonds we've formed, what kinds of bonds there are. It tells us about lone pair electrons, but it doesn't innately give us information about the bonds, what differentiates bonds between different elements. One of the improvements we can make to add some quantitative detail is we can include some information about how equally shared those electrons truly are between the two atoms in a bond. Now, if one atom is more electronegative, that atom is going to have more of a tug on the electrons, and they're going to spend more time near that atom. We're going to have a polarization of our bond between the elements. So we're going to, first of all, break this into two broad categories. We have covalent bonds, where the electrons are equally shared. And so if the difference in electronegativity is 0, we definitely have a covalent bond. Now, as the difference in electronegativity increases, by about when we get to a difference of 1.7, this is where our bond now has 50% ionic character. So the electron has been 50% transferred between one of the atoms and the other atom. This is a reasonable cutoff where we'll start calling this an ionic bond instead of a covalent bond. Even though it's reasonable, it's arbitrary. It could have been a little bit to the left, it could have been a little bit to the right. But this will help us to draw some broad categorizations of different kinds of substances and how they behave in different situations. Actually, this is not quite defined enough. We're going to go ahead and introduce another division here. We're going to define polar-covalent as something that's kind of in between ionic and covalent. And that's going to be something that has an electronegativity difference between 0.4 and 1.7. So this is about 10 or 15% ionic character, and then we get up to about 50% ionic character. Defines our polar covalent region. Now, remember that ionic bonds typically involve a metal and a nonmetal. Not in every single case, but that's a good tip-off that we're over here in the ionic region without having to calculate anything. Covalent bonds typically involve nonmetals when we encounter them. They can involve metals as well. So for an example, let's ask what kind of bond is present between boron and chlorine. So what we need to do is we need to calculate the difference in electronegativity. And if we look that up, for boron, it's 2.04, and for chlorine, it's 3.16. So we'll take the difference between these, and we always just look for a positive value. So you can subtract these in any order you care to, but just take the positive of whatever number you get. In this case, we get 1.12. Now, because 1.12 is between 0.4 and 1.7, that puts us in the polar covalent region. So this is a polar covalent bond. Lewis structures were initially developed by Gilbert N. Lewis with the idea of representing covalent bonding, but it's very easy to modify these to also depict ionic bonding, now that we're going to draw a distinction. But ionic bonding is a little bit different. We're actually moving electrons rather than sharing them, and we want to make sure that we represent that in our diagram. So for instance, what would be the correct Lewis representation of calcium chloride, this being an ionic compound? Our calcium chloride is made up of calcium 2+ ions and Cl- ions. And the way we're going to draw these ions in our Lewis symbols, we're just going to take the two electrons that calcium has, and since it's calcium 2+, we're going to peel those off. Chlorine has become chlorine minus, so we'll give it another electron. Now it has its filled octet here. And then for our Lewis structure, we are just going to draw these in conjunction. So we have two chlorines, each with a -1 charge, to go with that calcium 2+ ion. Our knowledge of the polarization of bonds can be used now to describe the presence of what's called bond dipoles. Now, in general, an electric dipole is any time that you have a fixed separation of charges. So you have a positive charge and you have a negative charge and some distance between them. Well, with our polar bonds and our ionic bonds, we have a transfer of charge because those electrons move and spend a little bit more time next to one atom versus another. And so we wind up with a partial positive charge on one atom and partial negative charge on the other atom, and they're a fixed distance from each other because of the chemical bond between them. So the way we're going to represent the partial charges is we use this Greek letter delta, and delta plus means you have a partial positive charge, delta minus means you have a partial negative charge. Fluorine, being the more electronegative element, is the one that picks up the electrons in this unequal bond. And so therefore, as extra electrons, as a negative charge. Hydrogen, its electrons have been pulled away, exposing more of its positive charge, so it has that partial positive charge. And the way that we're going to represent the bond dipole is as a vector, as an arrow with magnitude and direction. And the way that we're going to draw it is it's going to point from the more electronegative element, the one that gets negative charge, to the more electropositive element, the one that gets a positive charge. Now, a caution here, many introductory chemistry textbooks go ahead and draw this the other way. So they draw it going from the positive to the negative. Now, that's technically incorrect. A lot of times, because they know it's not quite right, they'll explicitly draw in the plus and the minus. I recommend just doing it the correct way. So as an example of this, let's consider the bond dipoles between phosphorus and oxygen, sulfur and bromine, potassium and chlorine. So start with the phosphorus and the oxygen. The first thing that we need to do is we need to determine whether or not we have a polar or an ionic bond, because that's the only case where we have a bond dipole. So we take the difference in the electronegativity of the phosphorus and the oxygen, get 1.44. So that's going to be in the polar covalent region. Knowing now that the bond is polar covalent, we know there's a transfer of charge here. Oxygen was the more electronegative element, so it's going to be the one that picks up the negative charge. The electrons will spend more time next to the oxygen, leaving the phosphorus deficient in electrons, so it will have a partial positive charge. And we'll draw our dipole going from the more negative element to the more positive element. You can almost think of it as just connecting this line from the minus sign to the heading here from the positive sign. Now for our sulfur and our bromine, take the electronegativity difference, we get 0.38. That's less than our cutoff that we chose of 0.4 between covalent and polar covalent. So this is going to be a nonpolar bond, and we're not going to assign it a dipole. We're going to say that there's no motion of charge between these two atoms. Our last case was potassium and chlorine. This is a metal and a nonmetal, which is almost always ionic, so that's very polar. And then we can draw the dipole pointing from the negative ion towards the positive ion.